Now, let us look into a topic called sampling. In the beginning of this subject, signals and systems, we assumed that there is an analog signal from which there is a discrete time signal obtained through sampling, but it was not clear at that point of time how the discrete time signal is obtained from analog signal. In the current section, we'll be mainly looking into how a discrete time signal is obtained from analog signal and also how the frequency domain representation of the signal gets modified when it is analog signal versus discrete signal. Let us consider a signal x of t which has a bandwidth of omega n. So without loss of generality, let us assume that the frequency domain representation of the signal x of t, that is x of j omega, looks as shown. Let us assume that the signal is conjugate symmetric and real, because of which x of j omega would be real as the signal is conjugate symmetric and conjugate symmetric as the signal is real. From this, we can say that x of j omega is real and even as shown in the figure. Suppose the signal x of t is sampled to get another signal xs of t. Let the sampling interval be t. The sampling of x of t is same as multiplying x of t with an impulse train, that is multiplying x of t with a signal sigma k equal to minus infinity to plus infinity delta of t minus kt. From this we see that the impulse train has impulses at the instants k into t where k belongs to z. From this we can say that the impulse train looks as shown. It is a sequence of pulses which are separated by t as shown in the figure. This is the impulse train, say s of t. From this, we can simplify the signal xs of t as sigma k equal to minus infinity to plus infinity x of kt multiplied by delta of t minus kt, where t is the sampling interval. Now we see that xs of t is obtained by multiplying s of t with x of t. From this we can say that the frequency domain representation of xs of t is xs of j omega, that is equal to a factor 1 by 2 pi multiplied by the convolution of x of j omega with s of j omega. This is because of the reason that multiplication in time domain is equivalent to convolution in frequency domain. So here x of j omega is frequency domain representation of x of t and s of j omega is frequency domain representation of s of j omega. But we know that s of j omega is equal to Fourier transform of s of t is equal to 2 pi by capital T multiplied by sigma k equal to minus infinity to plus infinity s of, sorry, delta of omega minus k into omega s, where omega s is equal to 2 pi by t. The s of j omega that we have written here is the frequency domain representation of s of t. From this we can say that xs of j omega, which is the convolution of x of j omega with s of j omega that we have written here, is equal to 1 by t sigma k equal to minus infinity to plus infinity x of j omega minus k into omega s. From this we can say that after sampling, the signal x of t will get modified as xs of j omega, where xs of j omega is the replica of, sorry, will have the replicas of x of j omega separated by k into omega s, where k belongs to z. From this, xs of j omega can be drawn as shown. At centered by 0, there is a x of j omega. Then centered by at omega s, there is another x of j omega. Similarly, centered at minus omega s, there is another x of j omega. Please note that because the bandwidth of the signal is omega n, the x of j omega at center will be between minus omega n to plus omega n. Now, if we consider the frequency band which is centered at omega s, that is actually from omega s minus omega n to omega s plus omega n. From this, we see that after sampling, we got excess of j omega, which contains many frequency bands similar to x of j omega, separated by k into omega s, where k belongs to z. But the signal excess of t we got here is still in time domain. So we do something called time normalization. This is by substitution of omega, by substituting small omega is equal to capital omega multiplied by t. So the signal that we get, sorry, the frequency domain representation that we get is in DTFT domain of, because after time normalization, the signal is in discrete time domain. From this, we see that x of e power j omega is equal to 1 by t sigma k equal to minus infinity to plus infinity x of j multiplied by omega by t minus k into 2 pi by t. From above, we see that x of e power j omega is periodic with period 2 pi. So, given a continuous time signal x of t, after sampling, we got excess of t. After time normalization, we got another signal which is in the discrete domain. Let it be x of n. From this, we can say that x of e power j omega is Fourier transform of x of n. Now, to reconstruct the original signal back, that is to get x of t from x of n, we see that by using a low pass filter, we with the frequency, sorry, with the cutoff frequency as omega s by 2, we can reconstruct the original signal back. That is in excess of j omega that we have shown. If we use a low pass filter, which has a cutoff frequency as omega s by 2. We see that we can reconstruct the original signal back. Also, please note that here the bands which are centered at omega s and 0 and so on wouldn't interfere with each other if omega s minus omega n is greater than omega n. That is, omega s minus omega n that we have marked should be greater than or equal to omega n. Then we can say that there wouldn't be any interference between the bands. From this, we can say that there is no aliasing. So, to avoid aliasing, the sampling frequency omega s should be greater than 2 times omega n, which is the cutoff frequency of the signal. This is called Nyquist sampling theorem. Also, please note that the low pass filter that we are using should have a cutoff frequency of omega s by 2 in time domain. To get the equivalent in discrete time domain, upon substituting omega s is equal to 2 pi by t, we see that the cutoff frequency should be equal to pi by capital T. So, if we follow the Nyquist sampling theorem, we can reconstruct the original signal x of t back from x of n. That is, we can get the continuous time or analog signal from the discrete time signal. Now, let us consider some problems related to sampling. Suppose there is a signal x of t whose cutoff frequency is 150 Hz. Then the Nyquist sampling frequency of the signal is given as 2 times the cutoff frequency, that is equal to 300 Hz. Now let us consider another problem as per which it is given that there is a signal x of t which has a bandwidth of omega x. There is another signal y of t which has a bandwidth of omega y. It's given that the sampling frequencies of x of t and y of t are sx and sy. If sy is equal to 2 by 3 sx, we need to find omega x divided by omega y. From the given data, we see that sy by sx is equal to 2 by 3, but we know that sy is equal to 2 omega y and sx is equal to 2 omega x. This should be equal to, so that the corresponding ratio should be equal to 2 by 3. From this, we can write that omega x divided by omega y is equal to 3 by 2. Now, let us consider another problem as per which it is given that there is a signal x of n which, when convolved with sine of omega c1 n divided by pi n, we got another signal, and which again convolved with sine of omega c2 n divided by pi n. It is found that this is equal to x of n convolved with sine of omega c n divided by pi n. We need to find the value of omega c here. We know that if there is a signal x1 of n which is equal to sine of omega c1 n divided by pi n, in the frequency domain, that is in DTFT domain, x1 of e power j omega is equal to 1 for mod omega less than or equal to omega c1, it is 0 otherwise. So The signal given, that is sin omega c1n divided by pi n, is a low pass filter with cutoff frequency as omega c1. From this, we can write that if x of n is convolved with sin of omega c1n divided by pi n, sorry, divided by pi n, in frequency domain, it is equivalent to multiplying the frequency band of x of n with a low pass filter of cutoff frequency omega c1, because convolution in time domain is equal to multiplication in frequency domain, which again in turn convolved with sine of omega c2n divided by pi n. So this again is equivalent to multiplying the resultant signal with a free resultant signal with a low pass filter of cutoff frequency minus omega c2 and plus omega c2. So after doing this multiplication in frequency domain, the resultant signal we get is in the range of say omega c minus omega c and plus omega c, where omega c is equal to minimum of omega c1 comma omega c2. So this can further be written as a operation where the signal x of n is convolved with a low pass filter whose cutoff frequency is omega c as given on the right hand side. From this, we can say that omega c would be equal to minimum of omega c1 comma omega c2. Now let us consider another problem as per which there is a signal g of t given as cos of 10 pi t, sorry 50 pi t multiplied by cos square of 150 pi t. We need to find the Nyquist sampling frequency of this signal. We can write g of t as cos of 50 pi t multiplied by cos square of 150 pi t, which can be written as 1 plus cos 300 pi t divided by 2. This is because we know that cos square theta can be written as 1 plus cos of 2 theta divided by 2. So g of t can be simplified as half cos 50 pi t plus half cos 50 pi t multiplied by cos 300 pi t. We know that cos A multiplied by cos B is equal to half in multiplied by cos of A plus B plus cos of A minus B. From this, we can simplify g of t further as half cos 50 pi t plus 1 by 4 cos 350 pi t plus cos 250 pi t. From this, we see that the cutoff frequency of the signal g of t is equal to 350 pi radians per second. Sorry, this is omega c. From this, the cutoff frequency fc is equal to 175 Hz. So the sampling frequency fs is equal to 2 times fc, that is equal to 350 Hz. From this, we can say that the Nyquist sampling frequency of the signal g of t is 350 Hz. Now let us consider another problem as per which it is given that Fourier transform of xi of n is equal to xi of e power j omega. Let xi of n be a low pass filter with cutoff frequency as omega ci. It is given that there is a signal y of n which is written as x1 of n convolved with x2 of n convolved with and so on xp of n, where p is a integer, positive integer. Now we need to find the bandwidth of y of n. We know that if y of n is convolution of x1 of n, x2 of n and so on till xp of n, then y of e power j omega can be written as the product of x1 of e power j omega multiplied by x2 of e power j omega and so on till xp of e power j omega, because the convolution in time domain is equivalent to multiplication in frequency domain. From this we can say that the frequency band of y of e power j omega is product of the frequency bands of x1, x2 and so on xp. So y of e power j omega will have a bandwidth which is equal to the minimum of omega c1, omega c2 and so on till omega cp. So the bandwidth of y of n is minimum of omega ci, where I runs from 1 to p. Now let us consider another problem as per which it is given that there is a signal x of t which has a frequency in the range of 7 kHz to 14 kHz, which has the frequency band in the range of 7 kHz to 14 kHz. From this information we need to find the range of frequencies in which x cube of t will be present. We know that x cube of t can be written as x of t multiplied by x of t multiplied by x of t. So from this we can write that Fourier transform of x cube of t is equal to Fourier transform of x of t convolved with Fourier transform of x of t convolved with Fourier transform of x of t, of course along with the scaling factor. This is because of the case that multiplication in time domain is equivalent to convolution in frequency domain. From this we can say that Fourier transform of x cube of t will start from 7 plus 7 plus 7, which is equal to 21 kHz. This is the starting point, and length of the Fourier transform of x cube of t is equal to 14 plus 14 plus 14, which is equal to 42 kHz. This is the length of Fourier transform of x cube of t. From this we can say that Fourier transform of x cube of t will be present from 21 kHz to 21 plus 42, that is 63 kHz. This is We came to this conclusion based on the property that multiplication in time domain is equivalent to convolution in frequency domain. So as from this property we can say that Fourier transform of x cube of t will be present from 21 to 63 kHz. Now let us consider another problem as per which it is given that there is a signal x of n is equal to cos of pi by 4n plus cos of pi by 2n. This signal is passed through a low pass filter of cutoff frequency equal to pi by 3. We need to find the resultant signal XR of n after passing the same through low pass filter. We know that the frequency domain representation of x of n for one band can be plotted as shown. The frequency domain representation will have impulses at plus pi by 4 and minus pi by 4. This corresponds to cos pi by 4n, and another set of impulses at plus pi by 2 and minus pi by 2. Here it is given that the low pass filter used has a cutoff frequency of omega c equal to pi by 3. So it is equivalent to multiplying x of n with a low pass filter whose band is as shown, that is from minus pi by 3 to plus pi by 3. From this we see that the resultant signal after multiplication, because the signal is passed through a low pass filter, so we have to do the convolution in time domain, which is equivalent to multiplication in frequency domain. So we multiply x of n and low pass filter to get another signal which will have only two impulses which correspond to pi by 4 and minus pi by 4. This is because the impulses at pi by 2 and minus pi by 2 get cancelled. So from this we can see that the resultant signal xr of n is equal to cos of pi by 4 n. So from this we see that if the given signal is passed through a low pass filter, the resultant signal that we get is cos of pi by 4 n. Now let us consider another problem as per which it is given that there is a signal x of t which is equal to cos 30 pi t multiplied by sin 150 pi t. We need to find the cutoff frequency of this signal x of t. We know the identity that 2 sin A cos B is equal to sin of A plus B plus sin of A minus B. From this we can simplify x of t as half multiplied by sin of 180 pi t plus sin of 120 pi t. We got 180 pi t by adding 150 pi t and 30 pi t, and we got 120 pi t by subtracting 30 pi t from 150 pi t. From this we see that the cutoff frequency of the signal can be given as omega x is equal to 180 pi radians per second. From this, the cutoff frequency fx in Hz is equal to omega x divided by 2 pi, that is equal to 90 Hz. From this, we see that the cutoff frequency of given x of t is equal to 90 Hz.